Next up, we have Michael Romeo talking about autoNGC, a framework, flight software framework for autonomous NGC.
All right, thank you. Good afternoon, everyone. My name is Mike Romeo. I'm the flight software lead for autoNGC. Today, I'm going to be talking about how we're bringing onboard autonomy to navigation, guidance, and control. So first, I want to talk a little bit about some of our motivations for going onboard and autonomous for NG&C. So the first one is obviously, if you put in some of the non-recurring engineering costs up front to introduce autonomy, you're going to have reduced operations costs overall. So this means that you can do more missions for cheaper. Second, we want to reduce our reliance on ground-based assets. So you hear a lot about how the space networks are becoming oversubscribed. And as more missions go up, it's only going to get worse. So we want to move a lot of the NG&C functions on board to kind of help reduce some of the loads on the space networks. And also, Earth-independent operations has been emerging as a kind of a big theme in a lot of NASA's Moon to Mars ambitions. And finally, and I think this is the most exciting of the three, is that we want to enable missions that were either very difficult to do before or not even possible. So one example is distributed systems missions, where you have multiple spacecraft that you want to all work in a coordinated manner. And of course, communications limited missions. So if you're out in deep space and you have some tough navigation requirements, this is really where autonomy is going to help you out. So now I'm going to talk a little bit about the autoNGC project. So as I mentioned, we're working to bring NG&C on board and make it autonomous. And since we're out of Goddard, I'm sure you could have guessed it, we're using the core flight system. And we're in the spirit of CFS, we're bringing extensive modularity and reuse to our flight software apps for autoNGC, and we're also extending that to hardware. So we want to make it modular and reusable for different navigation sensors like GPS receivers or navigation cameras. So in its current state, the kind of the three major components of the autoNGC project are the flight software framework. So this is all being enabled in flight software. And since we're going autonomous, we need to have a very robust simulation test bed and set of analysis tools. And finally, we have a reference hardware platform. So we want to design a flight processing system that we can be reusable for future autoNGC missions. So we're designing to target a lunar navigation scenario. So we're focusing mostly on the navigation aspects. We're looking at guidance for onboard guidance for future missions. But given the importance of lunar navigation and just how hard it is to do lunar navigation around the moon, this is kind of a big enabler for the Artemis program. So we're trying to bring sort of unprecedented navigation performance to lunar missions. So for this reference mission that we're targeting, we're incorporating multiple different navigation sources. So we're starting with GPS, but at the moon, it's really weak signal GPS. You can't really get a strong signal from the GPS lobes out there. We're also introducing train relative navigation and limb-based optical navigation. So those are both optical navigation techniques where you use an onboard camera to take an image and extract navigation observables and measurements from those images. We're also using ground-based radiometric measurements in our one-way and two-way DTE, direct to Earth. And during maneuvers, we use accelerometer measurements. So when the spacecraft is performing a burn, we use the accelerometer to improve our knowledge of our position and velocity. And finally, given the importance of time in navigation, we have a rubidium-based atomic clock. So now I'll talk a little bit about the autoNGC flight software. So as I mentioned, we're implementing autoNGC as a collection of CFS apps and libraries. So we're focusing on hardware interfaces. So this is interfacing with our navigation hardware and sensors. We also have libraries or interfaces for existing navigation libraries. We developed an onboard ephemeris library, so we can query onboard ephemerides for planetary bodies. We're in the process of developing an ephemeris prediction app, so we can propagate our state forward and predict our future states. And finally, given our focus on autonomy, we're in the process of developing a robust fault management system. We're targeting NPR Signium 50.2D Class B, so we want to be certifiable up to Class B. And finally, one of the key enablers of autoNGC is all the existing Goddard software products. So obviously, CFS is a big one. We also use the Goddard Enhanced Onboard Navigation System, or GEONS, and the Goddard Image Analysis and Navigation Tool, or GIANT, for optical navigation. So I won't go too deep into CFS, since I'm sure most of you are familiar with CFS, but CFS is focused on bringing reusable app-based architecture to flight software. It includes the core flight executive, operating system abstraction layer, and the platform support package to make it easy to run your flight software on different operating systems and hardware platforms. And CFS is used extensively both within NASA and other government agencies and private industry and academia, so really extensive heritage. Now I'll talk a little bit about the Goddard Enhanced Onboard Navigation System, or GEONS. That is the navigation filter that we use for autoNGC. GEONS has heritage on the Terra, MMS, GPM, and NICER sextant missions. It supports a variety of navigation sources, so the ones that we use along with crosslink, celestial navigation, limb and centroiding measurements, and even X-ray pulsars. And GEONS includes a suite of ground tools as well for simulation and analysis capabilities. Now I'll talk a little bit about our optical navigation capabilities. So GIANT is a little bit more of a recent tool developed at Goddard. So it started as a Python library developed for ground use on the OSIRIS-REx mission. But given the success of GIANT, we ported it to C++ to make it more suitable for flight software. And we call that C-GIANT for CFS GIANT. And that's going to enable onboard autonomous navigation. It has state-of-the-art image processing algorithms for extracting navigation observables from images taken on board. So there's some examples of images. So there's a shape model of Bennu that was built using C-GIANT, and an example of how C-GIANT can extract the limb observations from a moon image. So it wouldn't be a complete CFS presentation without the classic lollipop diagram. So this is kind of the key apps that we use and that we develop for autoNGC. Down here at the bottom left is kind of our main navigation-centric apps. So we have, GEONS is our navigation library along with an interface. So it works with CFS. And our state prediction app and our ephemeris library both interact with GEONS. And then over here we have our GNSS interface. So we're using the NavCube 3 mini GPS receiver, which is also developed by Goddard. And we are interfacing our clock both with the GPS receiver and autoNGC. That way, we're keep them both in sync. So you'll notice here we actually have two instances of CFS. We communicate over the Software Bus Network app over SpaceWire. So we use two flight processors. One is the primary flight processor, and one is more of a high-performance flight processor, more for the image processing side. So you see over here, we interface with our camera, and we have our interface with C-GIANT for doing terrain relative and limb-based optical navigation. So since terrain relative navigation is one of the more cutting-edge features on autoNGC, I'm going to go a little bit more into detail about how we do TRN. So our images are captured by the onboard camera, and what we do is we build a representation of where we think we are and what we think the camera should see, and then we correlate the actual camera image with what we think it should be, and we use that to refine our navigation, our position. So the onboard maps that we use are provided by the Luna Maps project. I'll talk a little bit more about that next. So LunaMaps is the Lunar DEM Mapping, Modeling, and Validation Project. It's part of NASA STMD's Game-Changing Development Program. So a lot of the existing moon maps from the Lunar Reconnaissance Orbiter, or LRO, are focused on scientific uses. So one of the big goals of LunaMaps is to create maps that are more suitable for terrain relative navigation and hazard detection. So they're mostly focused on digital elevation maps, or DEMS. And the LunaMaps team is currently working on releasing these DEMS and software to build these products in the near future. So as I mentioned, we're running on 2 processors. So we leverage NASA's SpaceCube line of flight processing systems for our reference hardware design. So our SpaceCube 3 Mini processor is the primary flight computer that has an AMD Kintex FPGA. We use a RISC-V soft-core processor, and we run RTEMs on there. And we are prioritizing reliability and uptime. So we do all of our critical operations on the SpaceCube 3 Mini. For our high-performance flight computer, we're using a AMD Zynq 7020. We're running on the Cortex A9 processor. It's an ARM processor, so it gives us a lot of performance. We're using Linux there, and that's primarily for our optical navigation, since a lot of the image processing algorithms can be a little bit computationally intensive. So we want to isolate that from sort of the critical operations that are done on the 3 Mini. And as I mentioned before, we use the SBN, or Software Bus Network app, to send the navigation measurements from the high-performance processor to the primary processor. So this is the hardware box that we designed. So this is what we plan to make reusable for future missions that use autoNGC. So we have 5 cards in the box. So as I mentioned, the SpaceCube 3 Mini and the SpaceCube Mini Z. We also have the low voltage power card. We have a configurable I/O card for various navigation sensors, and of course our backplane. So it has a mass of less than 2.5 kilograms, and it consumes about 15 watts of power and nominal operations. We consider this to be low swap. So now I'm going to talk a little bit about how we do simulations for autoNGC. So as we simulate our navigation, guidance, and control, we kind of have this simulation pipeline. So it all starts with filter tuning and configuration. So this is primarily done by the navigation subject matter experts. So they use a MATLAB interface for GEONs. And they basically tune the hundreds of parameters in GEONs till they get the results that they like. They look at plots. And then once we have good navigation performance, they generate a set of config files and then publish those as packages on GitLab for the future simulations to use. So once we're happy with once our filter is tuned and we're happy with those results, then we start doing software in the loop simulations. So we have our flight software, CFS with autoNGC, loaded in a Docker container. And we have our simulator read flat files with navigation data, along with our configuration that was developed in the filter tuning step. And then what we try to do there is to reproduce the results that we got during filter tuning, but with the flight software in the loop. And then once we're happy with the results, then we do processor in the loop testing. So again, here the goal is to reproduce the results done during software in the loop. But in this case, we're focusing on testing the performance of the algorithms and making sure that they can run on development boards for the space cubes that we're using. So this kind of gives us space cube-like performance since it's using the same FPGAs as the flight hardware. And we try to reproduce the results in a more flight-like environment. Then finally, our hardware in the loop simulation, we migrate to actual ETUs of the SpaceCube processors, and we use a lot more high-fidelity simulators. So this is where we bring our rubidium-based atomic clock into the loop, and we also use more high-fidelity GPS simulators and the camera ETUs. and we make sure that when we have more high fidelity measurements, we can still see those same results as we did in the previous steps. So a little bit about our simulation environment. So we simulate our orbit using the 42 simulator, and we save those all to flat files. As I mentioned before, for TRN, we use data from Luna Maps. And using Giant, we can generate synthetic images of the moon to simulate images coming from the camera. So we have a camera emulator that we wrote, or we provided with our current position and attitude, and it will generate a sort of a fake image of the moon that's suitable for optical navigation, and then we feed that into the flight software for it to extract navigation observables. And then we use Geon's data gen simulation tool to generate our GPS measurements. So that reads in the data from the flat files, and it will generate the actual signals that the GPS receiver will receive. This is all driven by our SimAll tool, we call it. It's written in Python, and it runs the whole simulation. It's developed as a set of Python packages, and we send CCSDS formatted packets over UDP to the flight software to simulate what the flight software will see in flight. It also provides data to the camera simulator. We're also working with John Lucas and his team to bring NOS-Cube support. So in the future, we want to be able to simulate autoNGC and NOS-Cubed. So the autoNGC lab, so this is where we do a lot of our high fidelity simulations with high fidelity simulators, our ETUs. So this is located on campus at NASA Goddard. So our big goal of the lab is to advance the TRL of autoNGC. We do this with high fidelity GPS simulation, image simulation. As I mentioned, we use our rubidium-based atomic clock, and we have a whole bunch of development boards and ETU in there to do these high fidelity simulations and tests. So this is kind of a look at what our high level overview of our hardware in the loop simulation environment looks like. So at the center of it all, we have the autoNGC ETU. And as I mentioned before, we're using the NavCube 3 mini GPS receiver. So we use a GPS signal generator to send GPS signals to the NavCube to simulate our current position. And we have that all synced up with our rubidium-based clock, and it also syncs with the flight software. We have our camera ETU, which captures the images and sends them over to the flight software. And of course, we have our ground system to collect telemetry so we can do post-processing and see the navigation performance of our current scenario. So a little bit about our release roadmap. So we've been developing autoNGC over the past 6 or so years. So started out with research and development, a lot of prototyping and just proving out the technologies and sort of low TRL tests. We explored multiple different use cases just to kind of explore how the technology works in different scenarios. So right now we're in the process of advancing the TRL. So we're rewriting a lot of our prototypes with more flight software standards. And as I mentioned, we're doing higher fidelity simulations. We're focusing on one main use case to focus on making it more certifiable up to NPR 50.2D Class B. And then finally, in the future, as we sort of finish up our TRL advancement and get autoNGC into a more flight-like state, we want to explore how to make autoNGC more available. So we have a lot of CFS-based tools that we use to develop autoNGC that we hope to open source at some point. But given a lot of the potential export control restrictions around guidance, navigation, and control software, we intend to try and make autoNGC available for U.S. government-affiliated entities in the future. So what's next for autoNGC? Right now we want to explore new capabilities and partnerships. So if you're interested in working with us, we're definitely open to hearing it and love to see what kinds of new technologies we can bring to autoNGC. We're also exploring some flight demonstration opportunities to help bring us up to TRL 9 someday. We're always looking to add more measurement types to autoNGC. So we're looking at adding LiDAR support, celestial navigation, and crosslinks. A lot of this GEONS already supports, so we're looking to enable that along with the autoNGC test bed. We're also looking into the G of autoNGC, guidance and maneuver planning. So right now that's kind of in early R&D. So we're looking to sort of prototype the guidance side of autoNGC and do simulations and raise the TRL there. And we're looking to improve our planning and scheduling capabilities and to introduce as much autonomy as we can into the system. And finally, I just want to acknowledge the autoNGC team. As you can see, we have a very multidisciplinary team across multiple different branches and divisions at Goddard, and an ambitious project like autoNGC wouldn't be possible without the kind of collaborations that happens with a multidisciplinary team like this. So on that, thank you all for your time, and go ahead and open up to questions.
Hey, thank you. Josh Sherbrooke from Stoke Space. I'm wondering if you could speak to where your autonomy config lives. Is it part of the same certification process? And then is that something you can change in flight?
So that's something that we're actively designing and improving on. So we're developing sort of a CFS executive app, so sort of a reusable mission manager. And we plan to kind of standardize how we handle mission planning and how we tie that into our fault management, and also how we can enable the sort of decision making that comes with autonomy. So that's definitely something that's kind of in progress right now, and we plan to kind of have that more fleshed out over the next few months.
Okay, thanks.
We have a question online. Wondering if it matters. Used to call GNC and now NGC is the name.
So yeah, it's kind of interchangeable. Yeah, we get that a lot because it's usually GNC, but a lot of people around Goddard use NGC. So I'm not really sure why we went with autoNGC over autoGNC. So I guess I don't really have a good answer for that one. It's probably the hardest question I'll get all day. Sure.
Hi, yeah, Isaac Rowe from Jacobs. Can you talk more about the TRN imagery generation? What resolution do you have, and how fast are you able to generate the imagery? Like, is it suitable for real-time simulation?
That's a great question. So I'm not sure what the resolution is, but we've been able to bring our time up to about, I think it's about 5 to 10 seconds per image generation by using GPU programming. So I know we use ray tracing with Vulkan for that. Yeah, if you want to reach out to me, I can get you some more information on that. I can get you in touch with our optical navigation subject matter expert.
Yeah, that'd be great. Thank you.
Sure.
There's another question. You mentioned that high-performance computer communication with other onboard computer using the SBN application through SpaceWire. Is this functionality already available on the public SBN repository?
So I think that the SBN repository does include a SpaceWire module. I know that we had to make some updates, I think, for the most recent version of CFS. So I'm not really sure if those are up on GitHub yet. But we can certainly, talk to the team that's making those updates and see if we can, push those out to open source at some point.
Thank you. So more questions. If you could please share later the public SBN URL. Somebody is looking for it.
Okay, yeah, I think it's github.com/NASA/SBN, I think. Yeah, but I can share that in the Slack just to make sure.
All right, very good. Follow on some other question regarding Giant. Was the camera ETU images simulated by an optical EGSC or just simulated?
So right now we are simulating them all in software, but we are looking for how to actually bring that camera ETU into the loop. So it might be as simple as putting the camera in front of a monitor and putting the image on the monitor and taking a picture so we can test the camera hardware. But we are actively exploring how to improve that camera in the loop simulation.
Very taking a while. We still have a minute or so. We can take a couple more questions. What's the criteria for validating the navigation of autoNGC when testing?
So, a lot of that falls onto the navigation subject matter experts. So a lot of missions will have navigation requirements. So a lot of it will be, simulating, GEONs, our navigation filter with the MATLAB interface and just running a bunch of simulations to try and get within the mission's, allowable required navigation tolerances. A lot of that kind of dictates, what kinds of measurement sources we'll use. So if we can't get the required navigation accuracy, then, we might have to add another navigation source or explore, improving, how much TRN we do or something like that. So, a lot of that falls on the navigation SMEs to kind of decide, what specific sensors we'll need and, how we'll reach that, those navigation requirements kind of given to us by missions.
Last question, is there any non-determinism introduced by the autonomy features?
Not yet. So for now, we want to keep the risk low as we explore our TRL advancement. So we are keeping it mostly deterministic, but of course, in the future, we would like to do some research with some more non-deterministic approaches to autonomy. So that's definitely an area for research. So that's probably a few years off for us, but we want to design the system where will be modular enough to kind of allow us to implement some of these cutting edge autonomy features and to see how they perform with autoNGC. So it's definitely a future work.
That's it for questions. Thank you, Michael.
Right. Thank you.